Welcome to our technical deep dive into VMware High Availability, or HA. In today's virtualized infrastructure, resilience is non-negotiable, and VMware HA stands as a cornerstone technology. Its primary role is to automatically restart virtual machines on healthy hosts if a physical server fails, minimizing downtime and disruption. But behind this seamless recovery lies a crucial mechanism: admission control. This gatekeeper ensures that enough resources are always available to handle unexpected failures. In this video, we'll break down how admission control works, why it's essential, and how it impacts your cluster's capacity planning. Let's start by understanding the basics of admission control and its pivotal role in high availability. Admission control is the unsung hero of VMware HA. While HA's automated VM restart grabs the spotlight, admission control quietly enforces the rules that make this possible. Its job is to guarantee that, at any given moment, your cluster has enough spare resources to accommodate all workloads in the event of a host failure. It does this by reserving resources and preventing overcommitment, ensuring that the promise of high availability is always kept. Without admission control, HA could not reliably restart VMs after a failure, making it a critical component of any resilient virtual environment. VMware HA keeps a vigilant eye on every ESXi host in your cluster. It uses a combination of network and data store heartbeats to monitor host health. If a host stops responding, HA springs into action, initiating a failover process to restart affected virtual machines on surviving hosts. But this process only works if there are enough resources available. That's where admission control steps in, ensuring that failover is always possible by maintaining reserved capacity. This proactive monitoring and resource management are what make VMware HA so effective. At the heart of VMware HA is a simple but critical question: are there enough spare resources in the cluster to handle a host failure? Admission control is designed to answer this question with precision. By enforcing resource reservation policies, it ensures that your cluster never overcommits and always has the capacity to restart VMs if a host goes down. This guarantee is what sets VMware HA apart as a reliable solution for business continuity. Admission control isn't a one-size-fits-all mechanism. Instead, it offers three distinct policies, each with its own logic and impact on cluster capacity. The first is the host failures cluster tolerates policy, which uses a slot-based method. The second is the percentage of cluster resources reserved policy, offering more flexibility by letting administrators set aside a specific percentage of CPU and RAM for failover. The third is the dedicated failover hosts policy, where one or more hosts are kept idle, ready to take over in case of failure. Understanding these options is key to choosing the right policy for your environment. The host failures cluster tolerates policy is foundational to VMware HA's traditional behavior. It calculates failover capacity using a logical unit called a slot. This method is straightforward, but can have a significant impact on how many VMs your cluster can support. In this video, we'll focus on this slot-based policy, exploring its calculation process in detail and highlighting its strengths and weaknesses. Let's dive into a real-world scenario to see how it works in practice. To make things concrete, let's analyze a 4-host VMware HA cluster. This cluster has a total of 160 GHz of CPU and 1,024 GB RAM, with the host failures cluster tolerates policy set to 1. 3 virtual machines are running, each with specific CPU and memory reservations. VM1 reserves 4 GHz of CPU and 8 GB RAM. VM2 reserves 2 GHz of CPU and 16 GB RAM, and VM3 reserves 3 GHz of CPU and 4 GB RAM. These reservations will directly influence our slot size calculation. With this setup, we're ready to walk through the 5-step HA slot calculation process. The concept of a slot is central to the slot-based policy. A slot represents a unit of failover capacity, defined by the largest CPU and memory reservations among all powered-on VMs in the cluster. It's important to note that the slot size is not based on an average or a single VM, but on the highest reservation values found. This means that even if only one VM has a high reservation, every slot in the cluster is sized to match it. This approach, while simple, can lead to inefficiencies, especially in mixed workload environments. To determine the slot size, we look for the single largest CPU and memory reservations among all powered-on VMs. In our scenario, VM1 has the largest CPU reservation at 4 GHz, and VM2 has the largest memory reservation at 16 GB. Therefore, the slot size for the entire cluster is set to 4 GHz CPU and 16 GB RAM. This uniform slot size will be used for all further calculations, regardless of the actual needs of other VMs. Now that we've established the slot size, the next step is to calculate how many slots can fit on a single host. We start by dividing the total cluster resources by the number of hosts to get per host values. Each host has 40 GHz CPU and 256 GB RAM. Next, we divide these per host resources by the slot size. 40 GHz divided by 4 GHz gives us 10 CPU slots, and 256 GB divided by 16 GB gives us 16 RAM slots per host. The limiting factor will be the smaller of these two numbers. A slot requires both CPU and RAM, so the number of slots per host is limited by the most constrained resource. In our example, each host can support 10 slots, since CPU is the limiting factor. To find the total cluster slot capacity, we multiply the number of slots per host by the total number of hosts. 10 slots per host times 4 hosts equals 40 total slots in the cluster. The next step is to apply the HA policy. With host failure's cluster tolerate set to 1, the cluster must reserve enough capacity to survive the loss of one host. This means we subtract the slots of one host, 10 slots, from the total cluster capacity. The result is 30 usable slots. This is the maximum number of VMs that can be powered on while still guaranteeing failover capacity. The final output of this calculation is the number of usable slots 30 inches our scenario. This number directly determines how many virtual machines can be powered on in the cluster, regardless of their individual resource requirements. It's a simple, predictable limit that makes capacity planning straightforward, but as we'll see, it comes with trade-offs. The number of usable slots has a direct impact on how many VMs you can deploy. In our example, even if a VM requires less than the slot size, it still consumes a full slot for capacity planning. This means that smaller VMs are forced to occupy the same resource footprint as the largest VM in the cluster, leading to potential inefficiencies and wasted capacity. One of the biggest drawbacks of the slot-based model is the outlier problem. If a single VM has an unusually high CPU or memory reservation, it sets the slot size for the entire cluster. This can drastically reduce the number of VMs that can be powered on, even if most VMs require far less. It's a classic case of one outlier constraining the entire environment. Because every VM is allocated a slot based on the largest reservation, many VMs end up using far more resources on paper than they actually need. For example, VM3 in our scenario only needs 3 GHz CPU and 4 GB RAM, but it's allocated a slot of 4 GHz and 16 GB. This leads to significant underutilization of hardware resources, especially in environments with diverse workloads. Let's put numbers to the inefficiency. VM3, which needs only 3 GHz CPU and 4 GB RAM, is allocated a slot of 4 GHz and 16 GB. That's 133% more CPU and 400% more memory than it actually requires. This quantified waste is the central trade-off of the slot-based model, and it can have a significant impact on your cluster's overall efficiency. The inefficiency of the slot-based model becomes especially pronounced in clusters with mixed workloads. If your environment hosts a variety of applications with different resource needs, the largest VM will dictate the slot size for all. This can severely limit the number of VMs you can run, even if most require far less than the slot size. The slot-based policy works best in environments with highly uniform workloads. For example, a dedicated VDI cluster where every VM has similar resource requirements can benefit from the simplicity and predictability of this model. In such cases, the risk of outliers is minimized, and resource utilization is much more efficient. For general-purpose clusters hosting a wide variety of applications, the slot-based policy can be a poor choice. The diversity of VM resource reservations increases the likelihood of outliers, leading to wasted capacity and reduced efficiency. In these environments, alternative admission control policies may offer better results. The percentage of cluster resources reserved policy offers a more flexible approach. Instead of basing capacity on the largest VM, administrators can set aside a specific percentage of CPU and RAM for failover. This allows for more granular control and can lead to better resource utilization, especially in mixed workload environments. Another option is the dedicated failover hosts policy. Here, one or more hosts are kept idle, ready to take over workloads in the event of a failure. While this approach is simple and easy to understand, it can also lead to underutilization, as the standby hosts do not participate in day-to-day operations. Selecting the right admission control policy depends on your environment-specific needs. If your workloads are highly uniform, the slot-based policy offers simplicity and predictability. For mixed workloads, the percentage reservation policy may provide better efficiency. And for environments where absolute reliability is paramount, dedicated failover hosts might be the best choice. Understanding the trade-offs of each policy is essential for effective capacity planning. The technical details of slot calculation have real business consequences. The number of usable slots determines how many VMs you can deploy, which in turn affects your ability to scale and respond to changing business needs. Inefficient slot allocation can lead to higher hardware costs and reduced agility, while efficient planning can maximize your investment in infrastructure. Effective capacity planning requires a deep understanding of your workloads and the limitations of your chosen admission control policy. Regularly review your VM resource reservations and look for outliers that could skew slot size calculations. Consider grouping similar workloads together or using alternative policies to optimize resource utilization and ensure high availability. Admission control policies are not set and forget. As your environment evolves, regularly monitor cluster performance and adjust policies as needed. If you notice persistent underutilization or capacity constraints, it may be time to revisit your policy choice or VM reservation settings. Ongoing monitoring is key to maintaining both high availability and efficient resource use. Leverage automation tools to help manage admission control policies and VM reservations. Automated monitoring can alert you to potential issues before they impact availability. Following best practices, such as documenting your policies and regularly reviewing resource usage, will help ensure your cluster remains both resilient and efficient. Be wary of common pitfalls when configuring admission control. Avoid setting unnecessarily high reservations for VMs, as this can inflate slot size and waste resources. Also, don't ignore the impact of outliers. One oversized VM can limit your entire cluster. Regular audits and careful configuration are essential to avoid these traps. To recap, the slot-based admission control policy provides a simple and predictable way to guarantee failover capacity in VMware HA clusters. By basing slot size on the largest VM reservations, it ensures that resources will always be available in a failure scenario. However, this simplicity can lead to inefficiency, especially in mixed workload environments. The slot-based policy is best suited for environments with highly uniform VM workloads, such as dedicated VDI clusters. In these scenarios, the risk of outliers is low, and the benefits of simplicity and predictability outweigh the potential for wasted capacity. For most general-purpose clusters, however, alternative policies may be more efficient. If your cluster hosts a wide variety of applications with diverse resource needs, the slot-based policy may not be the best choice. The risk of outliers is high, and the resulting inefficiency can limit your ability to scale and fully utilize your hardware. In these cases, consider using the percentage reservation or dedicated failover host policies instead. Let's compare the three admission control policies side by side. The slot-based policy offers simplicity but can be inefficient. The percentage reservation policy provides flexibility and better resource utilization in mixed environments. The dedicated failover host policy guarantees capacity but may waste resources by keeping hosts idle. Choose the policy that best aligns with your operational goals and workload patterns. In our 4-host cluster scenario, we saw how the slot-based policy calculates usable slots. With 160 GHz as CPU and 1,024 GB RAM and 3 VMs with varying reservations, the largest values set the slot size. After applying the failover reservation, we ended up with 30 usable slots, a clear, actionable number for capacity planning. The key takeaway is that admission control is essential for ensuring high availability, but the choice of policy has a major impact on efficiency. The slot-based model is easy to understand and implement, but may not be suitable for all environments. Always analyze your workload patterns before choosing a policy. For administrators, the best practice is to regularly review VM reservations and admission control settings. Avoid unnecessary over-reservation and be proactive in identifying and addressing outliers. Use monitoring tools to track resource utilization and adjust policies as your environment evolves. VMware HA is more than just automated VM restart. It's a comprehensive system for ensuring business continuity. Admission control is the mechanism that makes this reliability possible, but it must be configured thoughtfully to balance simplicity and efficiency. By understanding the details of slot size calculation, you can make informed decisions that maximize both uptime and resource utilization. As virtualization technology evolves, admission control policies are likely to become even more flexible and intelligent. Machine learning and advanced analytics may soon help automate policy selection and adjustment, further optimizing resource use and availability. Staying informed about these trends will help you keep your infrastructure ahead of the curve. In summary, the Host Failures Cluster Tolerates policy offers a simple and reliable way to guarantee failover capacity, but it can lead to inefficiency in diverse environments. The central trade-off is between predictability and resource utilization. By carefully analyzing your workloads and choosing the right admission control policy, you can strike the right balance for your organization. Our final recommendation is to match your admission control policy to your workload profile. For uniform workloads, the slot-based model is effective. For mixed environments, consider percentage reservation or dedicated failover hosts. Regularly review and adjust your settings to ensure optimal performance and availability. Let's quickly recap the key terms discussed in this video. VMware HA, admission control, slot size, failover capacity, and the 3 admission control policies. Understanding these concepts is essential for anyone managing a virtualized infrastructure and aiming for high availability. Here's a quick glossary. Slot is a unit of failover capacity defined by the largest VM reservations. Admission control is the mechanism that enforces resource reservation. Failover capacity is the reserved cluster resource for handling host failures. Percentage reservation and dedicated failover host are alternative admission control policies. Many administrators wonder how to optimize slot size or whether to use custom VM reservations. The answer depends on your environment. Always balance the need for high availability with efficient resource use. Regularly review your cluster's performance and adjust policies as needed to maintain the right balance. To wrap up, remember these best practices. Avoid unnecessary over-reservation. Monitor for outliers. Choose the admission control policy that fits your workload. And regularly review your settings. By following these guidelines, you'll ensure both high availability and efficient use of your infrastructure. In conclusion, VMware HA and admission control are powerful tools for ensuring business continuity in virtualized environments. By understanding the details of slot size calculation and the trade-offs of each policy, you can make informed decisions that balance simplicity, efficiency, and reliability. Thank you for joining us on this technical deep dive. For those looking to deepen their understanding, explore VMware's official documentation and community forums. Stay updated on best practices and emerging trends in virtualization. Continuous learning and adaptation are key to maintaining a resilient, efficient infrastructure. Thanks for watching, and good luck with your VMware HA deployments.